We are at the beginning of an exciting decade for space exploration, in which we will first go back to the moon. But we still don't have answers to questions such as how frequently do new impacts occur, or are there changes on the moon that we are not aware of? The task of this challenge is to scan 13 years of LRO diviners dataset to detect changes on the whole lunar surface, such as new craters and landslides, to answer those questions. This would help to provide targets for future exploration, as well as identifying potential hazards for future robotic and human missions to the moon in advance of Artemis. The Luxembourg Space Agency would like to thank FDL for organizing this inspiring program, and the Lunar team for taking up this challenge.
One of the science goals of NASA's Artemis mission is gaining an improved understanding of the moon's and our solar system's history. We still don't have answers to questions such as how frequently do new impacts occur? Is there present-day tectonic activity on the moon? Therefore, detecting recent changes of the lunar surface is very useful to NASA. I'm excited to see if we can use machine learning to identify the faint and transient signatures of features such as fresh craters, landslides, and tectonic activity. This research will ideally provide targets for future exploration, as well as identify potential hazards for future robotic and human missions to the moon. NASA would like to thank our partners, the Luxembourg Space Agency, and of course the amazing research team for helping pave the way.
Welcome, everybody. Thank you for being here, and thank you very much for having us. We are the Lunar Exploration Team, and we are hunting for fresh craters on the moon. The moon is often referred to as the archive of our solar system. The craters on it are billions of years old, and they can form as a snapshot into the past of our solar system. Alongside the craters, other features like the canyons on Mars and the basins on Mercury are the key puzzle pieces to understand how the planets came to be as they are today. But just like with the bones in paleontology, there's a very important task, and that is dating back to when these surfaces have been created. On the left side, we have a very young surface, on the right, a very old one. One thing that is very apparent is that the craters are much bigger and more numerous in the right one. And actually, by counting the size and number of the craters, we can establish how old these surfaces are. But there's one very important factor that is needed, and that is knowing how many impacts there are within a given time frame, the impact rate, and that is where we come in. The LRO, the Lunar Reconnaissance Orbiter, has been gathering data for 13 years, and we are trying to find within this data set if any new craters have appeared. Teams before us, researchers, have done this with the optical data, but there's a big limitation, which is the illumination conditions that vary too much after 2 passes. Because of this, only 6% of the moon have been scanned with this method. But luckily, there's also thermal data available, the one that we are working with. And there's a very important and interesting physical phenomenon happening during an impact. When an impact occurs, the center is heating up, but it cools back down very quickly within a day or a few weeks. The chance that the satellite is actually capturing this is extremely low. But luckily, the seismic wave at impact is disturbing the regolith, the moon dust around the center itself. This is then settling down at a lower density, and during the night, it will cool down much faster than the regular area. These cold spots, the large blue areas that you see, last for hundreds of thousands of years. Yes, and by spotting those, we're going to know if we find new craters. Our solution is called NEFTIS. It's the New Event Perceiving High Trust, High Yield System. And this is how we do it.
So we are going to use data acquired from a satellite. For this reason, we need to deal with the problem of data sparsity. So we decide to aggregate the information over the years to create a unique image for the before and after for every point over the moon. So for the before image, for every point, we take the earliest measurement. For the after image instead, for every point, we take the latest measurement. So after this data pre-processing, we are ready to apply our machine learning solution. Our first solution is based on a binary classifier. So we train a neural network to recognize if the input image is or not a cool spot. After that, during evaluation, if we want to check if a point corresponded to a fresh cool spot, we produce the before and after image for the point. If the prediction for the before image is no cool spot and the prediction for the after image is cool spot, this means that probably in that point a recent impact occurred. The second solution that we implement is based on an anomaly detection technique. So we use as training data the background noise, that is the difference between the before and after image. So we train our neural network to learn the distribution of the background noise. During the evaluation, so at this time, if the input image is very different with respect to the background noise, so with respect to the distribution learned during training, then the network will output a very high anomaly score. And this is a sign that a recent change occurred in that point.
For the evaluation part, we will only have 5 non-impacts. So for each of the impact, we're going to select a large area around the location. Then we're going to run our methods to see if we can find it. And then eventually we can verify that with optical images. So here is one example showing how big the evaluation site is. Then we can further zoom in to see the detail. So as you can see here, the blue dot, the green dot in the middle is the non-impact detected by the traditional methods. And the blue ones are going to be the candidates by the anomaly detector. So to keep in mind that anomaly detector is not only able to find the cold spots, it's also able to find other type of anomalies, such as landslides or even moonquakes. And lastly, we have the yellow ones are going to be the candidates by the binary classifier. So as you can see, both our methods are going to be able to recover the null impact in the middle. So we can further check the details of each single candidate. We can check the before and after thermal images, and we can also clearly see the cold spot is present from the difference image. And the last step is to check the optical image. So here, the white dot in the highlight region is the impact, whereas the black regolith around it is the sign of the cold spot. So remember that we said we have 5 regions to evaluate, and amazingly, we are able to find all 5 recent impacts with both our methods. So in summary, our tool is able to automatically highlight all the potential new impacts for any area on the moon. And we can also auto-generate all the relative informations, such as thermal images or optical images. It's also worth mentioning that the whole process is really fast. It's only taking less than a minute to evaluate the whole region, whereas the traditional methods could take days or even weeks. So in conclusion, detecting the new cold spots on the lunar surface is going to allow us to have a better understanding of the impact rate on the moon. And a similar methodology could also be applied to other celestial bodies, such as Mars. So in the end, it will allow us to have a better understanding of the history of our solar system. Thank you so much for listening.